In this problem, we're going to model a laminar flow reactor as having segregated flow. And what that means is we can envision small packets of material moving through the reactor without mixing with packets next to them. So each little packet behaves like a batch reactor. And so to calculate the conversion, we have to add up all these little batch reactors, and that then is based on how long they spend in the reactor, which is based on the residence time distribution. So this is the exit concentration from the reactor. We essentially are integrating over all these batch reactors. So let me write this down and then I'll explain what these terms are. So this is the batch reactor. So this is what the concentration as a function of time is for a batch reactor, in this case for a second order reaction. This is the residence time distribution for a laminar flow reactor. And so by summing all these together, we can calculate the exit conversion. So we're going to elect to solve this by differentiating the equation. We don't have to do it that way, but it turns out it makes it easy then to use polymath, which is good at solving differential equations. So if I differentiate this equation, then an important thing is the correct initial condition. At time equals 0, this is 0. So what this means, if we look at our original equation, if we integrate it from 0 to 0, the concentration, the average concentration will be 0. It's only when we add up over all the times we're going to get some finite value. And then the other term we need is this residence time distribution for a laminar flow reactor, and I'm not going to derive that here. Let me write it down. So the residence time distribution is such that it's 0 for time less than tau being the average residence time over 2. In other words, nothing leaves the reactor until that time. And then it's equal to the average residence time squared over 2 times the time cubed for t greater than tau over 2. So the last thing we need to solve this is the mass balance for a batch reactor, so we can get the concentration as a function of time. So minus k Ca squared for second order reaction. Well, this differential equation, the initial conditions, if we have batch reactor at time equals 0, Ca is our initial concentration entering the reactor, 12 moles per liter. So what I will do is solve these two differential equations simultaneously using polymath. That turns out to be a particularly easy way to do it. So let's look at the polymath equations, how they're entered into polymath. Now I should note that in this first equation, before we differentiate, we're integrating from 0 to infinity. Well, to solve the differential equations, we're going to use t equals 0, starting point, and then we'll pick some time. If it's not a long enough time, we'll pick a longer time. We're basically looking at what's long enough time that this value no longer changes, that we've accounted for to a pretty good approximation material moving through the reactor. Well, here's the polymath program where C batch is the concentration here, and C laminar is this Ca bar. I put in initial conditions. I've also included by using this symbol, number symbol. Everything after it is just a comment. And then in this simulation, I also calculate the conversion, what fraction of the feed is converted. Well, let's look at the plot. So you can see I picked the time long enough that essentially the concentration is constant. And if I read off the tables in polymath, I can get an accurate value for that concentration. And that value is 1.13 moles per liter. So the conversion is the entering value, 12 minus the exit value, over the entering value, 0.905. So we would say 90% conversion in this laminar flow reactor with segregated flow.